So today we're going to talk about the 3 laws of thermodynamics. We're going to go through it very briefly. We're probably not doing the entire subject much justice, so please keep that in mind when you watch the video. We're only skimming the surface. So the first law of thermodynamics tells us that it is a measure of heat energy that is released or absorbed when bonds are broken or formed during a chemical reaction at constant pressure. Those are the 2 operative words. If we are to draw the reaction coordinate as a potential energy diagram, if you have your reactants at the top and your products are at the bottom, meaning that they are lower in energy, if you're going from the reactants to the products during the reaction progress, energy is released, it is exothermic, and your delta H is less than 0, meaning it is a negative number. On the flip side, if your reactants are lower in energy and your products are higher in potential energy, the reaction is endothermic and the sign of the delta H is positive. There are 3 ways to calculate the enthalpy of a reaction. The first one that we learned about was using the heats of formation, which tells us the amount of energy that is required to make 1 mole of a compound from its elements in their standard states. So for example, carbon is graphite, sulfur is another one, fluorine, iodine, bromine, oxygen, hydrogen, all those, when they're molecular diatomics in their standard states, are 0. However, one thing to note is that the oxygen atom, on the other hand, requires 249 kilojoules per mole of energy. And the reason for that is because it takes energy to actually break the O2 bond of the molecular diatomic. So the way you would actually calculate the enthalpy of the reaction is you're using tables that are either in the back of the textbook or you'll be given the values in a testing situation in a table format, and you are taking the sum of the heats of formations of the products multiplied by their stoichiometric coefficients, which is what the little n stands for. The sigma stands for the sum of, and you subtract it from the heat of formation of all the reactants. Again, the sum of all the reactants multiplied by n times their stoichiometric coefficients. The second way to calculate delta H of a reaction is we use Hess's law and heats of formation, and this we use if a reaction occurs in several steps. So we take the sums of the energies of the absorption or release of the energy in all the steps. So for example, the formation of carbon monoxide is a 2-step process, and for the 2 half reactions, we are given a delta H1 and a delta H2. The whole point is that most of the time when we are given the delta H's of the half reactions, usually they're given to us as being negative, as being exothermic. Most of them usually are. The whole point of this is that you'll have to notice that the 2 half reactions have to cancel out, the reactants and products of the half reactions have to cancel out, and the overall reaction has to be what's actually specified in the question, the balanced overall reaction equation. So in this case, we can cancel out half a mole of oxygen, because here we started off with 1 mole and I crossed off the half, put a half there because that's what's left over. And we could cross out carbon dioxide from the products and the reactants. When we sum them together, we actually get carbon plus half a mole of oxygen gives us carbon monoxide, and the delta H of that reaction is negative 111 kilojoules. So if a reaction is reversed, the delta H sign gets reversed. So the delta H for example, of this reaction reversed would be carbon monoxide plus half a mole of O2 gives us CO2 gas. The delta H of that reaction will be negative 283 kilojoules. So if you have to reverse, you just flip the sign. And if your equation has to be multiplied by a constant, so let's say if I had to multiply this by 2 or by 3 in order to make everything cancel out nicely and to get my overall reaction, I would have to multiply my H's by that exact same constant. The third way is using the summation of bond enthalpies, and you'll be given bond enthalpies in either a table format, or it's also something, a value that could be found in the back of the book. So BDE stands for bond dissociation energy, and that tells us how much energy is actually needed to break a bond. So same process, to get the delta H of the reaction, you have to sum the bond dissociation energies of the broken bonds subtracted from the sum of the bond dissociation energies of the formed bonds. So for example, if we're looking at water, H2O, you're adding 1 mole of H2 plus half a mole of O2 in order to give you 1 mole of H2O. So the way you set up your delta H reaction is your BDE, your bond dissociation energy over here is for H2 is 400 kilojoules per mole, plus 495 kilojoules per mole is the bond dissociation energy value for 1 mole of oxygen, O2, but because I had a half here, I had to multiply it by the stoichiometric coefficient, which was a half. Subtract the bond dissociation energy multiplied by the stoichiometric coefficient, and I think this needs to be here. Oh no, it does. 2, sorry. This is 2, this 2 right here corresponds to the 2. Actually, I have to double check that if that's not a mistake or not for water. So 648 kilojoules minus 934 gives us overall negative 286.
Nice. So for the balanced equation, you have 1 water.
Yeah.
Yeah, so that would be a 1.
That's a 1.
Yeah. That's okay. As long as you get the idea across.
Whatever.
It's all right.
Yeah.
We're having a third board over here?
Uh,
Or did you go to the other one?
yes, that's right. Okay, so the second law of thermodynamics, again, we're only very briefly touching upon it, and second law of thermodynamics, we're introducing a new term which is called entropy. And entropy is really a measure of the randomness and the disorder contributed by the energy that is no longer available to do work. And work is the uniform motion in atoms. So when we're talking about entropy, we can't talk about absolute entropy. We can only talk about delta S. So S is the symbol for entropy. When we talk about delta, we talk about the change in entropy that occurs from the products minus their reactants. And the value becomes positive when more randomness or more chaos actually occurs. So in general, entropy is predictable in many cases. So for instance, liquids have more entropy than solids. Gases have more entropy than liquids or solids, because if you imagine gas in its actual gaseous state compared from a liquid, going from a liquid to a gas, the molecular motion is much more chaotic, much more random. It's not as ordered as it would be in the liquid or in the solid state. Also, particles in solution have more entropy than something that isn't dissolved. So for instance, a solution of salt water is way more chaotic than liquid water itself, where you're only talking about the hydrogen bonds. As soon as you introduce a particle into solution, you're disrupting the hydrogen bonds, and you are creating more randomness, more chaos, and more disorder, more entropy. 2 moles have more entropy than 1 mole of any substance, and that goes for anything. The more of something you have, the more entropy that exists. Delta S for the reverse reaction will have the same magnitude but opposite sign. So for example, if a forward reaction has, let's say, plus 150 joules of energy as entropy, the reverse would be negative 150. That's what that means. Third law of thermodynamics, or Gibbs free energy, it combines both laws, the first law and the second law, and it combines enthalpy and entropy. Together they form free energy, and when we're talking about And free energy, we're talking about Gibbs free energy, and the sign is delta G. Again, when we're talking about free energy, we're talking about the change in free energy, going from products to reactants and from reactants to products. When we're talking about free energy, we're talking about spontaneity. Whether if a reaction is spontaneous, it means that it is actually likely to happen. So free energy is the energy that can be harnessed and used to do work due to a chemical reaction. Okay, so we're continuing on with free energy, and again, free energy today we're discussing, again, skimming the surface. Please keep that in mind. This subject is way more in depth than we're actually covering. So when we're talking about free energy, and when we're actually combining enthalpy and entropy, the reaction that we're using, or the reaction equation that we're using, is delta G equals delta H minus T delta S. This is a key mathematical formula that you will need to use every time you're doing delta G calculations. So, here's a general trend of what actually happens. Again, this doesn't apply to every situation, but it is a general trend if you want to do a quick estimate whether something's going to be spontaneous or not. So for instance, the best situation that could arise in order to give us a spontaneous free energy change is that our change in enthalpy will be negative, which means that the reaction is going to be exothermic. The change in entropy is going to be positive, which means that entropy is increased, because that is more likely to happen in the universe. And the free energy change, delta G, ends up being a minus sign as well. So after you've plugged in all the numbers, your overall sign should be minus, and if the overall sign is minus in your delta G, that means that the reaction is spontaneous. It is definitely likely to happen. But those aren't always the cases. So for instance, let's say again that we're starting with a reaction that is exothermic, but now our entropy has decreased. We've made a structure that has way more order. This doesn't necessarily mean that the overall free energy change won't be spontaneous. It can be. It can be if your delta G ends up being minus, and this could likely happen at low temperatures. At low temperatures, the T delta S factor will not the delta S will not determine the overall spontaneity of the reaction. It is because your enthalpy slightly overpowers all of delta G, which can give you a spontaneous reaction. If, however, on the other side is that if you have a high temperature, so then your T delta S factor starts to become, starts to play a bigger role in the overall delta G, and then you may end up getting a positive value, which would mean that you have a non-spontaneous reaction. If now, let's say that you have an endothermic reaction, and endothermic reactions actually do exist in real life, we have experience with them. If entropy is increased, which is favorable, at low temperatures, we could end up getting a non-spontaneous reaction. However, at high temperatures, we could get a spontaneous where the overall delta G would end up being 0. And finally, if your reaction is endothermic, your delta H is positive, you have, let's say that now you have decreased entropy, which means that you've made something that is way more ordered, has more structure, and your delta G value ended up being a positive, that means that the reaction is non-spontaneous. It is not likely to happen. One thing to point out here is that what I want to say is that just because a reaction is spontaneous, that doesn't mean that it's going to happen in a time frame that we could actually imagine, or in a time frame that would be meaningful for us. So the reason why I'm saying that is because just because a reaction is spontaneous, that doesn't mean that it is kinetically favorable. So for instance, the decomposition of diamond to graphite, it ended up being that the delta G is a negative value, it's negative 2,900 joules. It is a spontaneous reaction, but that doesn't actually mean that it would happen in a time frame that is meaningful for us. Even though the process is spontaneous, diamond turning to graphite, that doesn't mean that it is actually going to happen in our lifetime. So please keep in mind that kinetics and thermodynamics are two different things, and let's not confuse them. One more thing I'd like to mention, if your delta G is equal to 0, that means that you are at equilibrium. And we will discuss equilibrium in more detail in the next unit.